right, thank you for all coming here, and you can hear me, right? And for the kind introduction. It's always nice to be coming to talk about our research to a group other than a conference, because you get very refreshing and different sort of questions. Sort of clash with my plans of going out to protest the fall of British democracy, but I decided I'd had enough tear gas for a lifetime when I was a teenager. So here I am. So this is a talk that about something that's about a year and a half old, but it's still, I think, quite relevant. And I think it's an interesting topic to share with a wider community of machine learning practitioners because it's exemplifying an emerging paradigm within reinforcement learning research, in particular with regard to applying reinforcement learning techniques to grounded language acquisition, whereby we're not just satisfied with training agents within a closed environment, but also jointly learning the notion of what it is to reward those agents for doing the right thing. And I'll illustrate that all through a variety of examples. There's very little mathematics in this talk, and whatever mathematics there is will be explained to depth. So this is, all work is done with usually some talented interns. Here top left we have Dmitry Badenow, who was my intern a summer and a half ago, and a variety of other great former colleagues from DeepMind. So I'll start with a high-level illustration of reinforcement learning, not because I assume everyone has some sort of vague notion of what reinforcement learning is. If not, this is a very gentle introduction, but also just to illustrate what we're diverging from. So reinforcement learning is the idea of training a policy or a way in which an agent is going to act in the environment by having it act on an environment from which it receives observations or states, and it also receives from the environment for each action or time step a reward. And the reward is an indicator of how well it's doing at a particular task. The rewards might be very sparse, so they might come at the end of a game of Go saying you won or you lost, or there may be some degree of shaping, heuristic, noise, uncertainty to ascribe to the reward. And reinforcement learning agents use this sort of setup without too much loss of generality in order to be able to train a policy so as to maximize expected reward. In a sense, reinforcement learning is about credit assignment because the reward doesn't tell you what action you did helped the most. It just tells you you're doing the right thing right now. And the algorithms deal with basically going from that signal to a sort of credit assignment signal, which allows you to train the policy. Feel free to interrupt if there are questions or if I'm going too fast or speaking absolute trash. So reinforcement learning, especially the deep variant, whereby the policies are modeled by artificial neural networks or fairly complex function approximators, has made great strides in the last 5 years. So here's an illustration from DeepMind's original work on DQN, which allowed policies overnight and now in a matter of minutes on modern sort of hardware to play various Atari games such as Pong or Breakout at a superhuman level. It's also been applied to sort of more traditional games with a very large branching factors, like the game of Go, which was considered by many to be sort of one of these, beyond the horizon problems where human heuristics and gut feeling would always sort of beat the ability of machines to search extremely large state spaces. But by applying deep reinforcement learning along with Monte Carlo tree search and some distillation techniques, researchers at DeepMind, not me, figured out a nice way to sort of basically constrain the space that you need to search in order to be able to find near optimal play, which famously led to DeepMind's AlphaGo beating Lisa Dahl, I guess one of the top players in the world in 2016. Beyond that, deep reinforcement learning has unlocked a whole new sort of field of research and training agents to exhibit complex behavior in a variety of increasingly realistic environments. So one example is DeepMind Lab that was produced by DeepMind, as you might guess. So in DeepMind Lab, agents are embodied, meaning that they have a first sort of person perspective of the world. They receive from the environment a pixel observation of their viewpoint and a reward signal, and get to act on the environment by moving as you might do in a video game. In fact, it is implemented in a video game engine. So they can strafe, move, change their viewpoint, and jump and crouch, amongst other things. But effectively, the important thing here is that the agent controls how it perceives the world. And this has been used as an environment for a whole host of experiments, but some of the more interesting work happening in the last few years is this work by my friend and colleague Hermann and some of his associates, where they trained situated language agents. So in this sort of setting, the agent is interacting in one of these 3D worlds, and it receives an instruction that tells it what it has to do, such as find the red object next to the green object. And then it observes its world through the stream of visual input as described before and gets to control what it sees by moving itself through the world. The environment designers in this sort of context specify the parameters of the experiment. So this means some things like the general layout of the maze that the agent is going to encounter during training, the possible objects that it might see, and also the form of the language instruction which describes how the agent can obtain rewards. So what sort of instructions it's going to receive. So this means that even if the language is fairly limited or templated, the precise world that the agent can experience is going to be chosen at random from like billions and billions of possible options. This is a cross product of the size of the language, the possible configurations of the environment, and if you really want to take it to the extreme, the particular positioning of the agent, which is going to give it a novel, if not familiar, experience of the world. And so to give you some illustrations, here we see agents picking a magenta object in a green room, and so it moves to this purple comb. You find a green object next to the red object. Well, there's a green object, but it's not next to a red object, so it starts to look at another room. There's a bunch of distracting colors, and there's a red object and a green object, so it sort of starts to strafe towards the right thing. Here, pick the magenta object in the green room. That's the first one. So here's an illustration of a particular run of this policy after training. It gets told, find the sign object next to the blue object, and so the first thing it does is it goes into a room and finds a sign object, but not next to a blue object, so it runs off, and it goes into the next room, and then it finds the blue object and starts to move towards the sign object. And I'd like to illustrate a few things here. First, it's actually quite impressive from a reinforcement learning standpoint because a large number of actions are made until a fairly sparse reward is obtained. So these are quite impressive results. But it does showcase a few limitations, first of all, just of like this particular mode of training. So even though the agents, through the particular architectures we use, using long short-term memory neural networks, are enabled with the capacity to remember the past and to understand long-term dependencies, we notice these sort of degenerate effects. So for example, it's told to find a sign object next to a blue object, and you'll note that it always moves as to keep the blue object in its field of vision before moving to the sign object, because effectively this turns it into a Markov problem. You don't need to capture very long-range dependencies. You can act entirely based on the information that you see in the visual input. So this is just to highlight that there's still a lot of open problems in this area, such as trying to capture very long-range dependencies, very complex or structured dependencies, such as, find an object of the same color as the one you saw in the first room. That would be very hard. So this is quite an open area for research. Why is this kind of work where we just throw in language in the mix and reinforcement learning so important? It's not just, oh, well, we've taken sort of a classical set of reinforcement learning problems and just added language as an extra modality. It actually adds a whole new dimension of richness. First, when you are training agents to act conditioned on policies, they're effectively, they become multitask policies. They're not just capable of doing one thing well. They're not just capable of playing the game of Go or of finding, the red object in a maze. They're finding something conditioned on a program or on some instructions given by an expert, and they're capable of doing multiple skills as a result. The space of the tasks that these agents can execute is determined by the language. And on top of that, this adds a new axis of generalization. We don't just care about the fact that policies generalize to new, unseen, or slightly differently structured configurations of the environment, demonstrating that they haven't just memorized things, but actually acquired the skill of navigation. But here we also can test whether they generalize to new instructions. So assuming that our language is compositional, meaning that the meaning of the instruction is a function of the meaning of its parts, and that you understand the meaning of the parts, then having never seen the instruction, find the red object next to the blue object, but also next to the green object, you'd expect a good policy that generalizes on the linguistic aspect to be able to see this completely new task and do something sensible. So for combinatorially rich languages, such as natural languages, such as English, the space of tasks is large or unbounded, and generalization to new instructions is plausible because natural language is compositional. in large part. So to take this initial sketch of reinforcement learning whereby we train a policy by having it act on the environment and receiving a reward, we can add just an extra sort of set of arrows to define language conditional reinforcement learning, whereby the policy receives the instruction because it needs to be told. Yes? Well, everyone has a microphone at their seat? Okay.
Can you hear me?
Yeah,
Okay?
sort of, yeah.
So if you want to focus on compositionality and the reinforcement learning, why not start with a formal language like the lambda calculus or something instead of starting with natural language?
Well, in practice, so the question is why not? Why would we jump straight into natural language rather than dealing with formal languages where the compositionality can be properly analyzed? I mean, the short answer is that although what they use in these experiments looks like natural language, is in fact just a finite fragment of English, which is effectively has a formal structure. And I'll get onto why that's actually a requirement in their experiments rather than just using unbound freeform natural language. As to why we'd want to do something that looks like natural language, well, it looks cool, and ultimately, like a lot of people that we're trying to sell this idea to don't necessarily care about formal languages, but do care about like having agents that are going to be able to do something practical in the real world. So it sells well. If you're interested in the ability of RL algorithms and, in fact, supervised learning algorithms to understand formal languages, in particular mathematics, then I refer you to some of my papers on this, which explore that aspect of things. But here, natural language seemed like a sensible thing to do. So if you throw language, whether formal or natural, into the mix, yeah, the policy needs to receive the instruction because obviously it needs to know what to do. But the environment also needs to receive the instruction because it needs to reward the policy for doing the right thing given the instruction. If I tell it, go find a red apple, and it brings you a blue apple, if there's such a thing in the environment, then obviously you should say, well, that's a bad job. But if I told the policy, oh, go find me a blue apple, then it makes sense that the environment should say, good job. So the reward function is now just not implicitly a function of the environment state, but also of what the instruction given to the policy was. And that's where the difficulty starts to arise. So how do we design this reward function? Typically, in all these sort of RL settings that places like Google and Facebook and DeepMind have published on, games like Go or Atari, the reward function is given to you by the environment designers. But if we move to experimental settings whereby, whereby we're actually given some sort of new input, we're designing something from scratch, we actually need to implement that reward function. So if you're designing a reward function, the first thing you can do is write a full interpreter over the possible instruction language, whereby it makes sense for it to be formal or at least bounded because you need to understand its semantics. So the best case scenario if you're implementing the reward function is that it's going to involve a lot of source code because you're writing an interpreter which evaluates, it's getting louder, which evaluates whether or not the expression makes sense given a state of the environment. But if you want to train a policy or an agent that's going to understand natural language with all its ambiguity and underspecification and complexity, that's going to be very difficult because we don't actually have a complete formal model of natural language. In fact, it's a common philosophical sort of point of discussion whether or not this exists, and some people, such as Wittgenstein, believe that there is no such formal specification of English. There are other alternatives for defining a reward function, of course, so you can learn from demonstrations, and this is broadly known as the field of inverse reinforcement learning with particular variants like imitation learning, where you're trying to infer from expert demonstrations what the reward function underlying the task being demonstrated is. And what I'm going to present today is a kind of variant of that. You can learn from preferences or rankings. So there's work by Cristiano et al. Where they solicit binary feedback from humans given two trajectories or examples of an agent behaving. Which one do you think actually corresponds to the action better? And it turns out that from this binary signal, you can actually train policies to do well. So on the left, we have a policy that's learned to backflip solely from these bits of feedback. And on the right, trained in traditional RL methods from handcrafted reward in the environment. And it turns out the human feedback creates a significantly more stable policy. There's a bunch of different options, but today we're going to talk about learning to follow instruction-conditional policies from goal state examples. So here's a little illustrative case for this. You have bought a very expensive robot, and you want to get it to do something practical like fold your towels. if your bathroom looks anything like mine. This is not an actual picture of my bathroom. But you've paid a lot for this robot, so you're like, I'm going to get my buck's worth, and I'd really like it to do, like, I wanted to fold towels like they do in those really nice hotels where they have, like, shapes of swans and stuff like that. So you have an intended goal that might not be, something you'd expect the creators of the robot to have built it, unless they had particularly exotic tastes which matched your own. So instead, you hope that the robot is smart enough to be able to, from you communicating something about your intended goal, to learn this behavior. And here's what I mean. So you want to be able to just tell it, fold my towels in a fancy shape. How would we train such a robot to be able to acquire a skill corresponding to what your intent is, to what you meant by this completely new instruction it's never seen before? So one option, which I'll refer to as goal state cloning, is that you have an example goal, right? You perhaps have a single picture, or you happen to have fancy towels folded for you by an expert, and it has to be able to modulate your other towels in order to fit that image or a configuration provided by an expert. So it then acts on the environment, which I've exemplified by just doing this very clever Photoshop technique of color shading. And it tries to find something that matches kind of the geometry and arrangement that is seen in the expert sort of conditioning. So this is a sensible way of going about teaching a robot a new skill. But there's a few different limitations here. First, it's quite hard to learn this way in general because typically the environment in the example might differ. You might not have a perfectly folded towel, or you have a picture of it, and just trying to match that picture with a different shaped towel might be very hard. I tried this at home. It is very hard. It's very easy if you're doing this process to fit very spurious features. So the way we train policies now, especially with neural networks, they don't really understand the notion of what are the salient features in the picture you're showing them. They're saying, oh, I need to fit kind of that picture by manipulating this towel. So they might start to just care more about what the background looks like, or making sure that it's like showing the right bit of floor, or something that doesn't actually match your intent, which is get that fancy folded towel. And it's also hard for this policy to generalize along several axes, because it's basically learned this skill by trying to match your example, and it's not going to necessarily generalize to new towels. But more critically, it's not, from learning to fold towels in this way, it might not understand how to fold napkins in that way. Whereas I assume, and maybe I'm wrong in assuming this, but if you're good at folding towels to look like animals, you probably can hack it with a napkin for like a restaurant setting, right? So new skills will therefore require more human examples, and it doesn't seem like this approach is very scalable. So the solution that we're proposing here is we want the robot to learn from human examples not only how to achieve the goals you're feeding to it, but also to recognize whether or not a goal has been achieved. And I'll discuss how this allows greater generalization along these axes. So to illustrate this in our example, reward modeling instead would involve you having this intention, fold my towels in a fancy shape, and to train the robot to do this, we would give it multiple examples of what you mean by this instruction. And we want to let the agent, through these examples, learn a general sense of what the objective is rather than just try and achieve it. And then once it's learned this general sense of the objective, once it's learned to recognize what you mean by this, because it has examples of it, use that learned objective in order to train without the human in the loop, without further provision of examples. And if this recognition ability generalizes, so if you've shown it, here's how you fold towels, here's how you fold napkins, then maybe it's going to learn how to fold, serviettes, or fold a tie, or do something fancy by understanding that there's some compositionality to the language. So the question we want to address, given these desiderata, is what learning method allows us to achieve these goals and train a policy? So the method that we introduced in a paper about 8 months ago is called Agile, which we definitely didn't retrofit into a cool acronym. But it stands for adversarial goal-induced learning from examples. Forget that bit. Agile, it just sounds cool. And the idea is we're going to split the brain of the policy into of the agent into two components. One that deals with what you're trying to do, understanding what you're trying to do, and that's what we call the reward model, and the other which tries to understand how you're going to achieve it, which in traditional RL terms is the policy. And the reward model is going to reward the policy. To fit this into our earlier schema, I want to build back up from the original sketch of reward learning, reinforcement learning. In reinforcement learning, a policy acts on the environment, which typically is what gives you the reward for acting on it appropriately. Instruction-conditional reinforcement learning, you add the instruction to the policy in the environment, which gives a reward condition on the instruction. And Agile just adds this extra external reward model in 2 stages of training. So now an externalized reward model is going to be what feeds the policy the reward, rather than the environment implicitly doing so. So when we're training the policy, it receives an instruction and acts on the environment from which it observes states. And instead of the environment directly giving the reward, the instruction that was originally given to the policy and the states produced by the environment from being acted on are bundled up and fed to a reward model which acts as an evaluator. It just says, okay, given that instruction and what you've done, good job or bad job. This is effectively just an externalization of what was already happening within the environment. The second stage is training the reward model, and this is where the interesting bit comes in. So we freeze the policy in its current state, and we let it act on the environment, and we're going to add all the states that it produces by acting on the environment, along with the instruction leading to those states being produced, into a buffer. And we're going to heuristically assume that everything that goes into that buffer is bad, which is a sensible thing to do when the policy is initialized randomly. And on the flip side, we're going to assume that we have a data set of positive examples of goal states given an instruction. So that's produced by the human going on whatever website and finding a bunch of pictures of the folded tile. And the reward model is going to simply sample some positive examples from our data set and some negative examples from the buffer and learn a binary classifier. Simply learn to say, okay, I got an instruction and I have an observation of what the world looks like at some point in the policy acting on it. Is the policy solving the problem given by the instruction? And then the true label comes from the origin of that example. Did it come from the data set? Then it's a true. And if it came from the buffer, then it's false. So the only bit of formalization I'll show you is the actual decomposition of both of these objectives. So we have a joint optimization problem. We're going to want to maximize the expected reward, and this is simply a temporal discounted reward function, where the reward signal is simply going to be the thresholded binarized discriminator probability. So the reward model is a discriminator given an instruction and a state, produce a probability that it's a goal state. If it's greater than 0.5, we say that that's 1. If it's less, then we say that it's 0, that it's 0 reward. We add an entropy regularizer, as is common if you care about implementing this stuff. And then you want to maximize that. You jointly want to minimize the loss of the reward model in order to train the discriminator. And so this is basically just binary cross entropy. So you want to minimize the probability of the state being a goal state if it came from the buffer, and you want to maximize it if it came from the data set of the experts. So we'll return to why this formalization was provided in a second, because obviously if you really want to look at the dirty details, we have everything in the paper. But here's some experiments demonstrating whether or not this idea works. So we wrote a grid world that is simple, quote unquote, where the agent is controlling a gray-white cursor, which I don't know if you can see on the screen, but there's a little gray cursor here. Well, the gray cursor here, and it can move that up, down, left, and right. And also, it can decide whether to do an interaction or a no-op. And you can think of interactions such as being something like clicking and dragging. So it gets to move over the world. If it's over an object, it can click to pick it up, in which case it becomes white. And then when the cursor moves, it drags the object with it, and then it can interact again to drop it. So learn to click and drag objects in a 2D world. Seems pretty simple. When it's holding an object, we also added the constraint that it can't move over other objects, just to add a bit of complexity. And in this environment, which hopefully seems fairly clear to people, just click and drag things, we added some high-level tasks to train a policy to do. So the first is grid-Loo relations. We called it Grid-Loo as an homage to Terry Gwynegred Shrid-Loo, if you didn't get the reference. We implemented we designed a simple domain-specific language which specified what must be done. And so this, although it's a formal language, pertaining to your question, all the instructions can be interpreted in plain English, such as move a red rectangle to the north of a blue triangle. And they can be underspecified, they can be ambiguous, there can be several different ways of satisfying them, but they're usually fairly simple. The semantics of this domain-specific language relative to the environment is known to us, And we're going to use this in order to implement an automated sort of a reward function for the training of baselines and also for an automatic evaluation process. But crucially, we're not going to give it to our Agile agent, since the whole point is learning to replicate this reward. The syntax of the agent is also known and optionally can be used by learners if you want to explore different architectures that are syntactically motivated. So does this work? So if you're training it without actually showing it the actual reward that the semantics gives you, we do train policies, accurate policies, that can learn to move the red rectangle west of the triangle, to quickly move the blue triangle to the south of the green rectangle, even in the presence of two options, to make a blue object to the north of a rectangle, so that's underspecified. So it learns to actually follow instructions that it might not have seen during training, without ever having sort of seen the actual reward signal, just from having seen a few positive examples of some instructions within the language. Because we've basically just jointly trained a policy and an actual reward function, which is used in place of the environment reward. The second task, and we'll get on to sort of a bit more of an analysis of the results and some quantitative results in a bit, is something that we called Griddler arrangements, because Griddler Tetris made our legal department a bit nervous, because I guess it's still copyright. But so these shapes from a famous game from the 70s or 80s are the instruction set. So you get told, okay, make a triangle or make a snake or a diagonal line. Some of the shape names are going to be superclasses of shapes. Whoops. So for example, all the adjacently connected shapes or all the diagonally connected shapes. And optionally, you might get a color modifier. So you might just get told, make a triangle, and you see a bunch of blocks, and you need to make a triangle out of them. Or you might get told, make a green diagonal line, and there'll be some distractor objects of a different color, and you need to build the appropriate thing. And within this version of the environment, we never implemented a reward function. So if you wanted to train a normal RL agent, you would not be able to do it, because there's actually there's literally no reward function. There's no possibility that we accidentally leaked information from the environment to the policy. All that we did is we used a solver to produce a few examples of what we mean by, for example, triangle or diagonal red or green line. And these don't cover the entire state space, so you're going to see at training time and at test time some configurations of the environment, so for example, the colors or the actual number of blocks, which doesn't match what you see in the data set provided by the expert. So does this work here too? Well, you see here without reward from the agent, from the environment, but just from a few expert examples, it learns a fairly general policy that's capable of making a snake or making a triangle for some red blocks. If you really squint, it looks like a triangle. And therefore, without the provision of an environment reward, can still learn to jointly model reward and act appropriately. In the presence of distractor objects, it also learns how to make a diagonal red line or make a green snake moving around the objects due to the constraints. I'll talk a bit about the mistakes it makes here, but it generally works pretty well. It makes more mistakes when there's distractor objects because there's a limited time budget to solve all these problems, and it's actually quite a difficult reinforcement learning problem. But it's still amazing that it did this without environment reward for us. So how does this method of like jointly training a policy and learning a reward function compare to like traditional reinforcement learning? So this is, I guess, a more finesse point, but I want to get into it in detail. So when in the traditional context, such as the experiments provided by Hermann et al., when we train a policy, it receives an instruction, the instruction is fed to the environment, and the environment gives you a reward conditional on the instruction. And the only difference between this setting when it comes to training the policy and our setting is that the reward model is explicit. So if you look at these two diagrams, you can imagine that reward model being shown as an external box as just being implicit in the environment. And if you're agnostic to how that reward model is obtained, these two things are completely functionally equivalent. And this is an important point. This means that modulo the additional algorithm which teaches you how to jointly train the reward model, nothing changes with regard to how you train your policy. You can use exactly the same model architectures that work well in competitive RL systems. You can use the same reinforcement learning algorithms. Everything else stays the same. All that we've done is added a process by which, from the expert evidence, you can decide how to determine whether or not something is a goal state. So because in the first set of experiments we had an objective reward function implemented because we defined the semantics of the language, we can compare how this works quantitatively to competitive baselines. So here we compared it to A3C, advantage asynchronous actor critic, which is how at DeepMind we obtained some state-of-the-art results in the Atari games in 2017. So the blue line is A3C, the competitive baseline. The black line is Agile, so exactly the same network, exactly the same training process, except the reward model comes from the reward signal comes from a jointly trained reward model. And the green line is A3C with additional sort of reward signal coming from a reward prediction auxiliary objective from the Unreal paper. And this is like probably one of the most competitive baselines of the benchmarks at the time. It has additional information that we're not exploiting. So the first amazing result here is just about the environment complexity. So being given instructions like move the blue square to the north of the red triangle, if you look at this blue line, a very competitive algorithm which learns how to play Atari games really fast could not converge on a complete solution. It gets about 80% of the episodes at test time right. And that demonstrates that grid worlds are actually quite a good environment to test RL algorithms on. If you throw in instructions which change what you're trying to do every episode, it's very difficult to train a policy with the true signal from the environment to do the right thing, because reward's sparse, and what you're trying to do is always changing under you. So the high variance of these RL algorithms really comes to bite you in the butt. So surprisingly, somehow learning an imperfect or approximate reward model somehow helps with this significantly, and we're still trying to figure out why that is. And the second thing is that that Agile, so jointly learning the reward model and the policy, actually performs really competitively with a very, very strong baseline here. It goes up to about like 90% success rate, and is quite competitive with regard to the A3CRP. And the third thing is that we notice that it gets up to that point, and then it starts to get a little worse. So performance degrades over time until it stabilizes at something that's kind of in line with the original baseline. So why might that be? So if you remember how we're training the reward model, we're training a binary classifier by showing it a bunch of examples from what the agent is doing on the environment and a bunch of examples of what the expert meant by some instructions. And thinking that everything the agent is doing on the environment is bad makes a lot of sense early on in training. But then as you start to get better, as you start to train a good policy, it actually starts reaching goal states pretty reliably. That's the whole point of this exercise. And then that heuristic breaks down. You're starting to put positive examples in your negative example queue, and because it's machine learning, garbage in, garbage out, the discriminator gets worse, so the reward model starts failing, and therefore the policy gets worse, and then there's some equilibrium. So we need to fix this because we don't like this sort of behavior. So we added this additional technique called buffer rejection. So here we're going to use the reward model as a purging mechanism in order to clean up the data during training. And this is quite an interesting sort of machine learning problem in its own right. You want to train a model, but you don't trust all the data that you're feeding to that model. So you use a version of that model, which it might be imperfect, in order to assess the data that you're feeding it, and then change that data distribution and then train on it. That seems crazy, and it seems like it should fail, but it turns out that this is a traditional problem in machine learning about reasoning when you have partially labeled or partially noisy data. So there's probably a cleverer way to do this. But our really hacky technique, which worked quite well, is that instead of just sampling half of our batch of positive examples from the expert data and half of our batch of negative examples from the buffer, from the agent acting on the environment, we're going to sample a lot more from that purported negative example buffer than we need. We'll run our current discriminator on all those examples and rank them according to how much the discriminator thinks that they're positive examples. And we're going to only retain the lower proportion of that super batch in order to balance the batches. And so basically that introduces a new hyperparameter, which is what that proportion that we retain is. And it turns out the more aggressive you are about retaining, about rejecting things, the more stable the algorithm becomes. So when you're rejecting everything except the bottom 25% of the negative examples ranked by that method, you see that the accuracy of the reward model relative to the true reward goes up to nearly 100%. And how this translates into a policy, here's the blue line here is the A3C baseline, the top green line is the A3C RP baseline, and this purple line is our most aggressive rejection mechanisms policy, which goes up to the same level as the A3C baseline, and modulo this crash in our evaluation job, actually persists at about 100% accuracy. So you can, with this additional technique of filtering your data, produce a model that, without auxiliary objectives, performs competitively on this difficult reinforcement learning problem without ever having seen the reward from a handful of examples.
Could you just repeat again how you do the rejection?
So you basically say, I don't trust my negative examples fully, so I think that there's some, I assume that there's some positive examples in there. So I'm going to use the current state of my reward model, rank them by how much I think they're positive examples, and throw away the ones that are most likely to be positive examples. This seems crazy because you usually want things that are close to the decision boundary, so rejecting points that are close to the decision boundary should harm your algorithm, but by virtue of the way the negative examples are produced, they're always close to the decision boundary. They're always examples that are, the policy wanting to get to the goal and, missing it because it takes some time or because it's not perfectly perfect yet. So it turns out that creating that margin artificially through this rejection mechanism actually works. Yes?
So would you consider this like a metacognitive process? It's like reasoning about its past decisions to see how...
That would be an interpretation of it, I guess. I mean, I don't have a lot of cogsci background, so I don't know how to answer that question. But in a sense, it's reasoning about its past experience. I guess so, because it is using itself to reason about part of itself. I mean, the way usually people have tried to characterize it is it's a form of adversarial learning with an inverse reinforcement learning. So the sort of stuff you see within like producing images that look like cats but are in fact classified as dog. This is kind of like a converse of that. But yes, it's open interpretation, and there's probably a better way to do this. We did this under pretty limited time. So I need to wrap up because I'm probably running a bit short on time. I think I have like 4 minutes left. I want to introduce some additional experiments we did. So if you've trained a model, not just a policy which tells you how to act in the world, but a reward model which given a possibly new instruction or possibly new configuration of the environment, allows you to train the policy on that. Then we can do something called fine-tuning, which is where we freeze the reward model, we say it's good enough, but we continue training the policy when something has changed. Why would we want to do this? Well, first because we want to be able to verify generalization to unseen instructions. So we do things like hold out 10% of the possible instruction set, and we train the policy and reward model, and then we measure whether or not the reward model allows you to fine-tune the policy to perform acceptably on the remaining 10%. Now, what you want to do eventually is see like 1% of the instruction set and have a reward model that will generalize to the remaining 99%. And that's definitely for further work. But this shows that the reward model, certainly without having seen all possible configurations of the environment, but even without having seen all possible instructions, can exploit the compositionality of the instructional language in order to be able to train appropriately in line with a full data regime. But there's other sort of applications of this idea of a policy having an onboard reward model. So something that typically happens, for example, when we do sim to real, when we train robots when we train policies that we then want to implement on actual robots, is that something changes in the environment. Typically, the battery gets low, or the actuators get damaged, or it walks over oil, or something about its current environment doesn't exactly match the assumptions that we saw during training, and that usually invalidates the policy. So is there a way that we could have a mechanism whereby we could have an inside the agent reward model that allows it to, on the fly, adjust its behavior when something has changed? So we simulated the sort of scenario whereby like a robot's actuators are damaged or its battery is low, and a particular class of the objects in the environment is too heavy and it can't lift them anymore. So we took the original experiments, trained a policy to about 92% accuracy, and then we made all red squares, specifically red squares, not all red triangles or blue squares, only the red squares immovable. And so if you just evaluate the policy at that point, well, naturally it fails about half of the time. So its success rate drops because sometimes it needs to move something else to the red square, and it doesn't matter that it can't move the red square. But if the instruction requires it moving the red square, then it moves to it and it just stays there because it doesn't know what to do. But if we fine-tune the policy, we notice that we can recover some, if not all, of the of the original policy's performance. So a significant enough chunk that is statistically significant. By evaluating, the reward model is still 100% accurate. So at this point, the fact that we can't fine-tune the policy up to 92% accuracy for us is just a problem with optimization rather than something with this setting. And this is something that's also been accounted by people like Chelsea Finn, who does meta-learning to train robots in the wild like this. So to summarize, the method I introduced today, Agile, or similar kind of methods inspired by inverse reinforcement learning, give us a window into this new world of problems whereby we're going to be training general reward models under the assumption that reward models generalize faster and better than policies. And this is a sensible assumption to make. This sort of pattern is rife throughout human reasoning. It's easier to verify a proof than to produce it. It's a lot easier to sort of run a program than it is to sort of produce it in the first place. So like learning a policy directly from examples in a way that will generalize seems quite difficult, but learning this level of indirection where you only need part of your model to say, okay, that looks like a sensible version of this example I saw before, seems quite promising. And if we have reusable reward models of this nature, we can use them to train systems that can learn without explicit reward being implemented or even implementable. So this is kind of the motivation for this paper. How do we train an agent to understand natural language if we can't implement a formal reward function? Well, we just have people give examples of what they mean and hope that the reward model understands enough of natural language through those fragments to be able to, train itself to follow new instructions without you constantly having to hold its hand. We can also use this to train beyond human anticipated tasks. So if you have a combinatorially rich reward specification language, you could imagine that once the reward model is strong enough to understand new instructions from that language, that the policy could just train itself by sampling new instructions from the grammar underlying the language and then trying to solve those problems and sort of just self-teach itself by experimenting or playing in the world. And I dare say akin to how a child learns, but that's usually an abuse of cognitive scientists in the room always cringe when I say that. And then finally, if you care about AI safety, learning policies that really have to maximize reward according to the intent demonstrated by human behavior rather than the assumptions of the programmer who implemented the reward function, I think is a way to produce policies that align with human values and pragmatics and goals significantly more than if you just have a hand-coded reward function. And we have a bunch of examples of policies maximizing rewards in artificial environments according to what the reward given is rather than the spirit of the reward, so acting degenerately in order to solve the problem. So I think this is a first step, not necessarily specifically this method, but this class of methods is a step towards making training agents as easy as talking to them, interacting with them, playing with them, which is exactly how we want to ultimately train our agents rather than have to curate data sets all the time. So I hope you find this to be an exciting sort of new research direction within this branch of artificial intelligence. Anyway, you can read about the paper here, a very extensive appendix talking about all the methods and some cool modeling tricks, so please take a look if you care about this stuff. And thank you for your time and for listening. Yes.
So you talked about the final goal. What does the reward function capture? Is it similar to the synthetic reward?
So the reward function is, as I said, a binary classifier, which is an approximation of the true reward without actually seeing the true reward signal. And we suspect that, I told you earlier, or showed you in this plots, that the policy trained under it actually did significantly better than a policy trained under the true reward signal. So my interpretation of this, which we haven't experimentally verified, but we could visualize, is that it gives you false positives around the reward space, which actually help you train. So if you think about it this way, it's learning a visual, given an instruction, it learns a visual similarity kernel with the sort of instructions and rewards it's seen in the past. So when the agent gets close to the reward, it might trigger a false positive, which actually is a good false positive to get because it says, oh, you're getting pretty close, so that's better than not getting there. Whereas if you're taking the true reward, that would just get 0 and you'd only get a sparse reward for matching the exact objective. So by virtue of the fact that you have some smoothness of that similarity kernel over observations means that the agent can actually learn from nearly getting there rather than fully getting there, and therefore that we see significantly better sample complexity.
Right.
I mean, given the level of the language in the experiments we had, the answer is straight up no, in that none of the experiments called for abstractions beyond understanding like the superclass of like, diagonally collected, but even that you have enough data to learn it. So I won't make any bold claims, but
Can it?
well, from a philosophical perspective, I'm convinced that we learn language by having to align with the pragmatics of the community that we act in, according to later Wittgenstein's work. So this is much closer in spirit to that than into saying, oh, we learn language by someone constantly telling you, yes, that's right, or no, that's wrong. So you implicitly, jointly learn how to act, but also whether or not you're acting appropriately. So I think it's plausible that eventually we'll learn abstractions through this, but we definitely haven't done it in our experiments. Yes. I'll repeat questions if the microphones don't work.
So I'm not a philosopher, but I didn't really know about that Wittgenstein stuff, but wasn't the idea that following a rule is difficult because there are multiple interpretations of that rule? If we only have examples of someone following the rule to help us understand what that rule is, it's not enough, and we need to have a communal language beyond that.
Yeah, so Wittgenstein did talk a lot about rule following and like the ways in which we'd understand kind of like what the negative examples would be without necessarily having seen them. I don't remember my Wittgenstein well enough to like talk about how this directly relates.
If you're looking at your towel example, the Wittgenstein angle is you can't just give examples of towels.
Yes.
Because it might be that actually what you're doing is giving examples of flooring.
Right.
And that just giving examples is just never going to be enough.
Yeah, so we did try and show it, don't know if this is answering your question, but we did try this simply by giving it a data set of like positive and negative examples in the first place. And we found that the policies never learned appropriate behavior because they never had to really sort of align their negative behavior to something that was close to the positive behavior. They just would fit this limited experience and not generalize. Not sure if this actually answers your question, but from another point, we do think that the particular method that we chose might not work for problems where you'd have rules that don't admit negative examples explicitly. So if you have an instruction like go to the goal without stepping on red stones, or like drive the car to the destination without driving off a cliff, and it happens that you don't have anyone in your data set who is willing to drive off a cliff to provide good negative examples for your car driving, how would you learn the notion of something that blatantly violates that constraint if all you have is things that satisfy that constraint? And that's definitely an open problem that's not addressed by this particular algorithm that maybe speaks to the sort of nature of your question. So we can't claim that this is a complete solution to the general problem. Yeah, over there, just yeah.
Yeah, thanks very much for the interesting talk. What would be really interesting to see is if you can use this smoothness in the similarity kernel to increase the sample efficiency of the discriminator. So you start with very few samples, maybe just red triangles that you have to assemble or align. And then once the environment is visually close to that setting, you start to rely more and more on the high probabilities from the discriminator and put those into the training set and then retrain the discriminator.
Yeah,
because that is close to what we as humans would do, right? We would start with assembling a couple
a few
of blocks.
examples and start extrapolating to the
exactly.
generality. And I guess that speaks to the notion of like abstracting away from, you have something that's very specific and then learn a more general thing. Yeah, that'd be an interesting experiment. I think that speaks more to like improving the data the data efficiency of the discriminator. We do have experiments that try and measure the data efficiency. But nothing of that sort of curriculum-based nature, which would be interesting. But so many interesting experiments to do and so little time before NeurIP's deadline. So, or iClear in this case. I think I can take one more question, and then I have to go accept a delivery in an hour, so I have to go home. Yes.
Sorry, I couldn't cover everyone.
Thanks again for an interesting talk. So
I was wondering how difficult was the agent to train? You know, was there much variability between different seeds? Do you have to end up having to use, you know, some tricks to help it along?
So all the plots we showed were, I think, the average of 5 runs, and we show error bars, I think, in the actual paper. So you can view the variance of them. When we definitely didn't do the, unfortunately, usual trick in the RL community of doing n runs and picking the top 5. It is difficult to train. It's a difficult RL problem, but really, like, just having that accidental smoothing due to the fact that you're approximating the reward function really helps, and you can actually solve these fairly complex problems to an appropriate degree. In terms of other tricks, I mean, the main thing, and this is agnostic to the reward modeling aspect, but if you're doing instruction-conditional reinforcement learning and you need to have a way of conditioning on the instruction, that's a very difficult thing to do. And the common trick that not a lot of people seem to know about is that you don't want to, like, produce a representation of your observation separately from the representation of your instruction, concatenate those, and then jointly predict the action. Because that requires whatever is doing the observation to compress everything that's to be known about the actual. Sorry, that requires you to compress everything that's known, that's possibly knowable about the observation in order to, like, not throw away something relevant. To give you an example, if I show you a bunch of objects and I say, look for the red apple, as a human, you'll probably just start looking at red things, right? You don't need to care about everything that's on the picture. Rather, if I do the other way around, saying, okay, like, here's 1,000 objects with indices, for example, and then I hide them from you and I say, look for which index was the red apple. Like, you need to have remembered everything, right? And how this translates into architectures is you want to, like, condition as early or in the process of compressing or of processing the visual input, you want to condition on the instruction. So what we used is something that was developed in Mila called film, whereby the instruction modulates the biases of various activation layers throughout this. And that's a very simple thing to implement, which has a very powerful effect that I've noticed in other experiments we've done in language conditional RL. The details are in the appendix, but that's really, like, the main trick that really helps to train in language conditional policy. Okay, thank you so much.